Alrighty, my name is Matt Mukerjee, and today I'm going to be talking about practical real-time centralized control for CDN-based live video delivery. This is some work I presented at SIGCOMM this past year. But that's not really the point of the talk today. The point of the talk today is really going to be about combating latency in wide area control planes. So we all know that centralization can provide you with many major benefits. So these are things like better performance, better reliability, ease of policy management, things like that. But when you take the centralization out of, say, like the data center, scalability can be really hard in the wide area due to the latency. So where are these sources of latencies coming from? Well, it's really pretty obvious if you look at this in this older 4D model. So in the 4D model, you have a bunch of these things like routers in your network that form the data plane. And they take some statistics of things like link capacities, failures, things like that, and forward it up to our centralized controller in what's called the discovery plane. The centralized controller does some processing on that, which is referred to as the decision plane, and that tells it how these routers should be configured, which is then sent out through the dissemination plane. So when you take this kind of model, you find that it works really, really nicely when you have a really tight, low latency control loop. So for example, in something like a data center. But when you try to pull this abstraction out into the wide area, you start to realize that, it's going to be troublesome if I have a lot of latency in discovery. Maybe it takes a long time to figure out if an overlay link goes down. You're also going to say, I'm going to have a lot of trouble if I have a lot of latency in my decision process because maybe I need to compute over all of the routers on the internet. And as we saw in some talks this morning and a little bit this afternoon, you're going to be in a lot of trouble if you have a lot of latency in the dissemination when you're trying to put updates to these routers. So each of these has their own interesting set of problems you need to tackle. And in this talk, we're going to focus on what happens if you have a very high latency decision plane. And so in order to do that, we kind of need a context. We need a specific problem to solve. So when you start thinking about problems on the WAN, one that comes up that we actually just saw is traffic engineering. Okay? And people say, OK, well, we can solve this through centralization. And what you probably want to do is maybe use a linear program, which is exactly what we saw in the last talk. And this works out really well. It's very scalable. Your decision plane ends up being fairly low latency. So why don't we scope this to a harder problem? What happens if instead of more general traffic engineering, we're looking specifically at delivering live video? So in this case, the big worry that you come up with is your utility function is no longer, if I just throw more bandwidth at the problem, things will go better. Your utility function now involves discrete bit rates. So you can't just add 10% to this one flow and do better. So put another way, your utility function is now stepwise. OK, so if we take our same intuition of, this is just more a specific version of traffic engineering, we could solve this with optimization as well. But this time, it'll end up being integral. So we'd have to solve it with an integer linear program. And so as you might know, this doesn't scale very well, and we end up having a high latency decision plane. So I'm going to ask you to suspend your disbelief and say we're locked into this being the right way to go, because I think this opens up an interesting question, which is basically, if you have this high latency decision plane, how can you get around it? Okay, what are some solutions that you can do architecturally to get around it? So what we came up with was kind of taking the decision plane and splitting it into two pieces. We have a centralized piece that focuses on quality and cost management. And then we have a distributed piece that focuses on responsiveness to things like joins and failures. And so we're going to combine them together into what we're dubbing hybrid control in this case. OK, so first I want to give you some background on what specifically our context of live video looks like, and then follow through with our centralized piece and our distributed piece. OK, so live video delivery today on a CDN looks something like this. We have a data plane and a control plane, as you'd expect. Our data plane is made up of a bunch of server clusters, namely video sources, reflector clusters, and edge clusters. They're connected to each other over the wide area with overlay links. And video requests enter the system via the edge clusters. They're propagated up as HTTP gets to video sources, and different videos might take different paths up to the source. But the key idea is that once it reaches the source, it goes back down in the reverse path to as simple HTTP data responses. OK, so that's not all there is to it. Obviously, these requests come from some clients. Obviously, the overlay has some notion of capacity on every link, as well as a notion of cost to deliver data over those links. Furthermore, on our control plane, we have something going on there. And in the case of CDNs today, this is typically something a little bit more simplistic, like a DNS server. OK, so the overall goal we want to do is maximize our service quality while minimizing the delivery cost. And we'll see how we're going to do that with a centralized control piece. So as we've kind of seen in a bunch of other talks today, you can construct some toy examples that really make it clear that centralization is kind of the way to go with these kind of routing problems. So for example, if we have two videos up there at the top, this blue one and the red one, and you have two clients, one wants the blue and one wants the red video, if that blue video is seen first, it might take a path like this through the network. And you'll notice right away that we're now congesting that D to G link. So now, unfortunately, for our guy watching the red video, he's either going to not see it at all, or they're both going to suffer with a lot of buffering. So in order to get around that, it would be much better if we could do something like this, where we can just split our data accordingly through this other set of paths. But unfortunately, to do that, we need a global view to coordinate resources at this level, which kind of motivates our need for centralization. Yeah, yes?
So are these actually like circuits being set up in the bottom, or is this like this is a data chunks or something?
So these are think of them like forwarding tables. We're putting up forwarding tables, and we're just telling the clusters, request video from this node above you, as opposed to this other node. Yep. OK, so obviously we're going to get rid of our DNS, and we're going to throw in our centralized controller. And what we want to do there is what I mentioned before. We're going to build an integer linear program. We're going to maximize maximize service quality while minimizing delivery cost, subject to some obvious constraints, like that we don't exceed link capacity and that you can only send videos that you've already received. And so this, kind of naively just turns into math. And I'm not really going to worry about that for the point of this talk. But it's straightforward, and it's what you would expect. So it turns out that this does pretty well. We can see that compared to what CDNs do today, we can roughly double the service quality and half the delivery cost. But of course, life is not great, because there's obviously no free lunch. And so in this case, it's that latency we were talking about before. So we see a graph here showing that the time it takes for a new client to join the system is actually very high when we ran experiments with nodes on EC2 and a controller across the internet at CMU. OK, so to make it really clear, why is this the case? Well, it's actually pretty straightforward. When you get a request at this edge cluster here, you have to sit and wait while you send a request to the centralized controller, and then wait for it to recompute what the new forwarding policy should be. But this, of course, is over the high latency internet, and that ILP takes a very long time to run. So we eventually get a thing back, but at that point, it's already been a couple of seconds to maybe minutes on large problems. So centralized control in this case will give us high quality, but we have slow join times. So what happens if we instead propose an alternate solution where we did it all distributed? Well, in this case, let's get rid of our centralized controller. And let's say we have some scenario we've already set up, something like this. Well, what happens when a new request comes into F here? Well, in our distributed algorithm, what we're going to do is just build a distance to video table at every cluster for every video. And this is basically just going to be like a distance vector protocol, but at the app layer. So the table looks something like this. At F for video 1, we could go up through C, and it would take, let's say, 2 hops to reach the video, because we have to go all the way up to B. And our path is bottlenecked by some value here, 1K. Or we could alternatively go through D. And since D is already actually receiving this video, it's only 1 hop to get to the video, and the path is bottlenecked by 800. And so what our decision here is just pick the shortest path that has enough capacity, in which case this is D. And so the nice thing about this is you can run this effectively immediately, because it's only computed based on local information. But as we saw before, since we don't have a global view, it's not going to be optimal. So of course, this question comes up with, we have these two competing approaches. Can we combine them in some way to get the best of both worlds? Namely, can we get rid of the slow join times of centralized and the lower bit rates of distributed control? So what that picture would look like is something like this. We'll have a set of these distance to video tables on every server cluster. And we'll also have our high latency centralized controller. And now let's say again we have our same scenario we saw before. So what will happen when that video request reaches F? Well, it will simply look at its local table and decide immediately to send it up to D. And then the video will be sent to the client, and he'll be happy because he joined immediately. But now, in the background, what F will do is send an update to the centralized controller saying, hey, I have a new request that came in. Centralized controller will do some sort of computation and figure out that, oh, hey, you know, that link up to D is really expensive. Let's avoid that. And in the future, please get your data through C, as we see here. OK, so this kind of approach is not without its own challenges. Of course, a worry would be things like forwarding loops. But in our scenario, this is pretty simple because we're always forwarding requests upwards in our graph, so that's trivial. State transitions, as we saw in 2 talks today, are pretty hard to do. But you can do things like versioning, where you just tag older configurations and forward on them. So you can rely on prior work for that. But the one that's actually the most interesting here is avoiding bad control loop interactions between the centralized control loop and the distributed loop, which is challenging in its own right. And so we don't claim to have solved this problem. I think it's actually a very interesting problem that I think requires more work. But we do have some points that we think help us avoid them. So what we do, for one, is that our centralized decision always has priority. So when a new decision comes in, it just basically flushes the tables out. Second is that distributed control only uses residual capacity in the network after the centralized control. Third is that the distributed control has no impact on current or future centralized decisions. And finally, the distributed control changes don't propagate more than 2 links up. So it turns out this works out really well for us. It certainly removes our join time issue. So as we can see here, with a fully distributed approach, we get better join times, right? But as you get into more load, it's not very stable and things go a little crazy. But in our hybrid approach, we get that nice low latency join times. And we actually do even better into heavier loaded scenarios as we're able to move things around within the network. So in conclusion, what we presented in this work is a possible solution for combating decision plane latency. And this was very much scoped to the context of live video delivery. But I wonder if this split of a centralized approach as well as a distributed approach combined together can be applied to other applications. And also, of course, I wonder, are there other solutions that can combat the same kind of problem of high decision plane latency? And so stepping actually one meta step back, I showed you this picture at the beginning that, OK, one big problem people try to solve on the way in is traffic engineering. And they say typically decentralize it and solve with an LP. And so we took that kind of logical step of, oh, we have a more difficult problem, but it looks pretty similar. So why don't we solve with an ILP? And that was pretty hard. So I wonder if, is there another kind of solution out there that's something very different than optimization that can solve this in a much more lower latency way so that we could avoid having to do these more complicated centralized plus distributed approach. And then, of course, the question then is, if you have an idea for what to do with that, can you sort of push that back up to the general problem of traffic engineering, and will that make that even more efficient as well? Alrighty, with that, I'd like to conclude, and I'm happy to take questions. Yeah, Bruce?
You had a slide where you showed sort of, I think, improvement in performance based on some empirical data gathered by Conviva. But,
yep.
I mean, maybe it's a dirty little secret, but one of the reasons why performance is suboptimal is because the CDNs, just like ISPs, take costs into account.
Yep.
You don't have any way of modeling how much more it would have cost to do this, do you?
Yes. It's actually, so we spent a while talking with people at Conviva about this as to what is their understanding of notions of costs for CDNs, okay? And we looked into Akamai stuff as well. And what you find is, as you have this multi-layer tree that we showed, right, where you have video sources, reflectors, and edge clusters, right? It tends to be the things that are closer to the core are more expensive, okay, in terms of delivery, okay? So we use that as our model in our simulation. And we are able to, from that loose model, figure out what the comparison to what current CDNs are doing for distribution versus what we could do. And you find that in certain scenarios, mainly like in large sporting events, where you have effectively you just build a big tree through the network. You can do a lot better than just using basic like DNS as opposed to using a centralized controller.
Well, I still don't quite understand. You don't actually have the CDN's cost.
Yeah, so we don't have the cost model because that's very sensitive data, right? Yeah, so we did our best to model what we did from.
What's your estimate? It costs more or less?
Oh, that it costs more to when you're in the core.
No, when you apply your solution.
Oh, yeah. So we're doing 1x compared to 2x.
You're saying it's going to cost only half as much and get better performance?
Okay, so the key point here, right, is what we were looking at is different usage models, right? So in the performance one, where we can get 2x is when we're looking at things like big user-generated scenarios, right? So things like Twitch, for example, where you have millions and millions of people who are all live streaming to 1 or 2 people, okay, mostly. And in those scenarios, we can do about the same cost but better performance. Whereas in other scenarios, like where you have one big event you're trying to stream, like a large sports game, we can do similar performance but with less cost. So that's the thing. So these aren't the simultaneous. And the interesting thing actually is honestly there's a trade-off there, right? So you can actually tune. Especially it's easy with the centralized part, right? You can tune whether you care more about minimizing cost or if you care more about pushing performance up. So you get that flexibility, which is nice. Does that help? Yeah.
It helps. It's just, I think, costs are not easy to model.
Sure. Yeah, we can take this offline and chat about it. And I'd be happy to hear from you more about, a better way to do cost modeling. Other questions?